Hello students, welcome to Kanakkiyal Thoondal. In this video, we are going to discuss TN State Board Class 12 Business Maths Exercise 10.2. Question number 1. The question is, what is the assignment problem? Assignment problem is nothing but a problem in which we'll be having m jobs to be performed on n machines. We'll be having m number of jobs and n number of machines. We have to allot each job to some particular machine in such a way that the total cost is minimum. This can be done with the help of the cost matrix. Cost matrix is nothing but a matrix Cij which represents the cost of doing ith job through jth machine. So if you are taking some particular in the cost matrix is nothing but a m cross n matrix actually. So in that matrix, if you take some C57 is nothing but the cost of doing fifth job through seventh machine. So using this cost matrix, we have to allot the jobs to the machines in such a way that the total cost is minimum. This kind of problems are called assignment problems. Then question number 2. Give mathematical form of assignment problem. So the mathematical form of assignment problem, actually our objective is to minimize our objective function, which is nothing but the total cost here. That is, we have to multiply the cost by the assignment value. Here our assignment value can be 0 or 1. If it is 1, if Xij is equal to 1, then it means that we are doing that particular job through that particular machine, and if Xij is equal to 0, then we are not allotting the job to that particular machine like that. So Xij is also a matrix of same order as Cij. So we have to multiply the cost times the quantity we are assigning, whether it is 1 or 0, and we have to take summation of it over j from 1 to n and over I as well from 1 to m. So this is nothing but our total cost for the particular assignment. And what are the constraints we have? Subject to the constraints, in assignment problem, the total demand for each row, each column is 1, and the total supply for each row is also 1. Because if we are taking some particular job row wise, the total supply is 1. It means that that particular job can be done using some one machine. It is a unique job. We can't split like 1 by 2 or 1 by 2. So it should be 1 always. So what I am telling is summation I varies from 1 to m, Xij should be equal to 1 for all j is equal to 1, 2, 3, etc. n. So let's say if we fix j is equal to 1, this summation is nothing but x11 plus x21 plus x31 plus x41. So first column values, if you add all the first column assignment values, it should be equal to 1. This is true for row wise also. Summation j is equal to 1 to n, Xij should be equal to 1 for all I is equal to 1, 2, 3, etc. m. So this is actually the mathematical structure of our assignment problem. And one more thing, we have to be very careful that the value of Xij can be 0 or 1 for all I comma j. For all I comma j, Xij should be 0 or 1. So this is the mathematical formulation of an assignment problem. Then question number 3. The question is, what is the difference between assignment problem and transportation problem? So let me tabulate some of the differences of transportation and assignment problems. Basically, transportation problem is nothing but distributing distributing the sources to destinations. So we will be having some number of quantities available in sources. We have to distribute them among the destinations. For example, we can break the quantities from sources. Let's suppose if we have some 60 number of quantities from source 1, we can distribute to two different destinations. But in assignment problem we can't distribute, we have to assign jobs to machines. Like if we are assigning the job means we have to give one only to the machine. We can't separate it like 1 by 2 and 1 by 2 or 1 by 3 and 2 by 3, like that we can't separate, but we can do that in the transportation problem. So that is the major difference first of all. Then second thing, in transportation problem the number of sources and the number of demands no need to be equal. Actually number of sources may not be equal to number of let me mark this as 1 and this as 2. So number of destinations, say we can have some 10 sources and only 2 destinations, but in the assignment problem the number of sources means number of jobs should be equal to number of machines. And third difference, unbalanced condition. We will say a transportation problem is unbalanced if total supply is not equal to total demand. Then we will say this transportation problem is unbalanced. And for the unbalanced condition for assignment problem is nothing but number of rows is not equal to number of columns. Exactly what we saw in the second difference, number of jobs is not equal to the number of machines. Then the transportation then the assignment problem is said to be unbalanced. Assignment problem is said to be unbalanced. And using the methods available here, northwest corner rule or least cost method, Vogel's approximation method, using these methods we can calculate only basic feasible solution, initial basic feasible solution only, they are not optimal. So the methods what we are discussing, these three methods are giving only initial basic feasible solution for a transportation problem. We have to use one more method, it is actually called Moody method, which is not in our syllabus, to find optimal solution. It means we have two stages of solving. First we have to find the initial basic feasible solution using northwest corner or least cost method or Vogel's approximation method. Then using Moody method we can find the optimal solution. But for assignment problem, using Hungarian method directly, we can find the optimal solution. Using Hungarian method we can directly find optimal solution. Then question number 4. The question is 3 jobs A, B and C want to be assigned to 3 machines UVW. The processing cost for each job machine combination is given by the cost matrix. We have to determine the allocation that minimizes the overall processing cost. We have 3 jobs A, B, C and 3 machines UVW. We have to give assignment for this particular scenario in such a way that the total processing cost is minimum. We are going to solve this problem using Hungarian method. So what is Hungarian method here? in Hungarian method, we have 3 different steps. Step 1, we have to find the least element from each row, and we have to subtract that particular element from all the entries of that particular row. For example, for the first row, the smallest element is 17. So if I subtract that 17 from all the other entries, including 17 actually, all the entries of that particular row will get 0 here and 8 here and 14 here. So this is what the first row of our new matrix. So what I am going to do is, I am going to draw ABC, UVW, and the new entries of the first row will be 0, 8, 14. Similarly for second row, the least element is 10. So here it will be 0, here it will be 15, and here it will be 6. So the second row entries are 0, 15, 6. And for the third row, the least element is 11. So 0 here, 1 here, 2 here, 3 here. So 1, 3, 0. So this is step 1. Step 2. Step 2 is nothing but doing the same process column wise. So U, V, W here and ABC. So if I take the least element of first column, it is 0 actually. So if I subtract 0 from any entries of that particular column, the entries remains the same. So what I'm coming to tell is, if we have 0 in particular row or particular column, then this process will give us the same entries. So 0, 0, 1. And for second column, the least element is 3. So if I subtract 3 from 8, I'll get 5. And from 15, I'll get 12. From 3, I'll get 0. And again, third column remains the same as we have 0 already. So in step 3, what I'm going to do, I try to give allotment. We have to search for the rows or columns in which we have only 1 0, exactly 1 0. For example, if I take first row, it has only 1 0, so I can give allotment like this. It means that we are allotting that particular job A to the machine U. So it means that we can't do A in any other machine, and we can't do any other job in the machine U. So it means that I have to strike out this 0. If I take the other 2 jobs and 2 machines, we can't simply allot, because the row of B doesn't contain any zeros. So this matrix is not enough to do our optimal assignment. So what I'm going to do, I'm going to do some modifications in this. So what are the modifications? First, we have to plot the lines in such a way that joining all the allotments. Say, if I give allotments for this 0 and this 0, we have to draw lines, the minimum number of lines joining all the allotted zeros. So these are the 2 lines. What I'm going to do here is, I'm going to find the minimum value. I'm going to find the minimum value of non-line entries. Non-lined entries. Now we have to subtract the value. Subtract from non-lined, and we have to add from the intersection entries. Remaining entries remains the same. So what I'm coming to tell here is, I have to find the least entry of the remaining 2 cross 2 matrix, which is 5 here. So I have to subtract this 5 from the non-lined entries 5, 14, 12, 6, and I have to add here because this is the intersection of those 2 lines. So now what I will get for ABC, U, V, W. So this 0 remains the same, this 0 remains the same, and this 0, this 0. So now what I have to do is 1 plus 5. So this is 1 already here, intersection of C and U plus 5, I'll get 6 here, and 5 minus 5 is 0, 14 minus 5 is 9, and 12 minus 5 is 7, 6 minus 5 is 1. So this is our new matrix. So in this matrix again I try to give allocations. So now what I have to do? I have to search for the rows or columns in which we have exactly 1 zeros. First row has 2 zeros, second row has only 1 zero. So that I am going to give allotment, and I have to omit all the other zeros of that particular column, as we can't do any other job in that machine U. So if I take the remaining, so this U is engaged, this B is given to U actually. So I have to see A row and C row, V column and W column. So from that we have only 1 zero in A row. I'm going to mark that. I'm going to erase all the other zeros in that particular column, and I have to mark the remaining 1 zero. So this is our optimal assignment here. So what I did is I gave job A to machine U and job A to machine V, job B to U, C to W. Here we have to find the total cost. So this plus this plus this. So the total cost is equal to 25 plus 10 plus 11. So 25 plus 10, 35, 45, 46. So the total cost using this assignment is nothing but 46 rupees, which is actually optimum. With the assignment A to V, B to U, and C to W. Then question number 5. The question is, a computer center has got 3 expert programmers. The center needs 3 application programs to be developed. The head of the computer center, after studying carefully the programs to be developed, estimated and computer time in minutes required by the experts to the application program as follows. So here we have programmers and here we have programs. So let us take 1, 2, 3 who are the programmers, and the programs are P, Q, R here, and this is the cost matrix. So assign the programmers to the program in such a way that the total computer time is least. So if I take randomly some this 110 means is nothing but the programmer 2 is taking 110 minutes to complete the program R. So we have to give allocations for each programmers for the particular programs in such a way that the total computing time is least actually. So using Hungarian method we are going to solve this. So Hungarian method contains 3 steps. Step 1, we have to choose the minimum entry of each row and we have to subtract the entry from all the entries of that particular row. For first row the minimum entry is 80. So if I subtract 80 from this entire row, I'll get 40 here, I'll get 20 here, I'll get 0 here, which is our first row of the new matrix. So let us write 1, 2, 3 which are the programmers, and P, Q are the programs, and the first row will be 40, 20, 0. And if I take second row, the minimum entry is 80 here, so it will be 0, 10 and 30. So 0, 10, 30 is the second row, and for third row minimum entry is 110. So if I subtract 110 from 110, I'll get 0, 140 minus 110, 30, and this is 10 here. So 20 here, 0, 20, 10. So this is the matrix. And step 2, I'm going to repeat the same process for columns. So 1, 2, 3, P, Q, R. So we have already 1 0, some zeros in first column. So if I take that minimum element, it will be 0. If I subtract 0 from all the entries remains the same. So I'll write the column as it is 40, 0, 0. and for second column the minimum element is 10. So if I subtract, I'll get 10 0 10, and already we have 1 0 in the third column, so the entries remain the same, 0 30 10. So in step 3 I'm going to give allocations. So what are the allocations we are going to give? So we have 40 10 0 0 0 30 and 0 10 10. We have to look for the rows or columns in which we have exactly 1 0. So if I take first row, I have exactly 1 0. So that's what I'm going to mark in box. It means I'm going to allot the first programmer to the the program R, and we have two zeros in the second row. It means that programmer 2 can be allotted to program P or program Q depending upon programmer 3. So if I consider programmer 3, we are going to allot him for the program P. So we are not going to allot any other person for the same program P. So I'm going to strike out all the zeros of that particular column if I mark some zero in any row, and the remaining only one program is B, I mean 2, and the only program is Q. So I'm going to allot that. So this is our step 3. Now I'm going to write my assignment schedule. Assignment schedule. So what is our assignment schedule here? So here we have programmer, here we have programs. So both of them I wrote in as a prog, and the cost. So for the first programmer I'm going to allot the program R with the cost 80, and for the second programmer program Q the cost 90 initial cost. We should not write these zeros or any other cost matrix in the step 1 or 2. We have to consider the cost matrix which is from the question. So for the programmer 3 I'm going to allot the only remaining program which is P. The cost is 110. So if I add them, the total cost will be 280. Total cost will be 280. So this is the optimal assignment. I mean this is not cost, actually time. The total time, optimal time is 280. Then question number 6. The question is, a departmental head has 4 subordinates and 4 tasks to be performed. The subordinates differ in efficiency and the tasks differ in their intrinsic difficulty. His estimates of the time each man would take to perform each task is given below. So this is a time matrix which can be treated as a cost matrix here as well. So how should the tasks be allocated to subordinates so as to minimize the total man hours? So we have to minimize the total man hours by giving some allotments from subordinates to that particular task. So we are going to solve this using Hungarian method. Hungarian method. So obviously, as like in the previous problems, we have 4 subordinates here and 4 tasks here. So the problem is actually balanced. So number of subordinates is equal to number of tasks. So the problem is balanced. It is a balanced assignment problem. So now step 1 of our Hungarian method. We have to choose the least element from each row and we have to subtract the element from all the entries of that particular row. For first row, the smallest element is 8 here. So if I subtract 8 minus 8, I will get 0, and 26 minus 8, 18, and 17 minus 8, 9, and 11 minus 8, 3. So the entries of our first row will be 0, 18, 9, 3 for P. And for Q row, the least entry is 4. So if I subtract 13 minus 4, I'll get 9, and 28 minus 4, 24, here 0, and here 22. So the entries are 9, 24, 0, 22, and the least element in third column, I mean third row, is 15. So it will be 0. So if I subtract 15, I will get 23. Here 4, here 3. So 23, 4, 3, 0 for the row R, and for the row S, the least element is 9 here. So if I subtract here, I will get 0, 17, 15 and 1. So 0, 17, 15 and 1. This is step 1. And step 2. In step 2, I am going to do the same process for column wise. So I have already 1 0 in first column, so the entries of that column remain the same. Actually we have 2 zeros, and for second column the least element is 4 here. So 18 minus 4, 14, 20, 0, and 17 minus 4, 13. And we have 1 0 in third column, so I'm going to write as it is. And we have 1 0 in fourth column, so that is also I'm going to write as it is. Now step 3. In step 3 I have to give allocations. So which to which we are going to give. So let me write the entries again. So 0, 14, 9, 3, 9, 20, 0, 22, and 23, 0, 3, 0, 0, 13, 15, 1. So we have to search for the rows or columns in which we have exactly only 1 0. If I take first row, it has only 1 0 here. So let me mark that, and I have to cross out all the zeros of that first column, because if I give box for that particular row, means I am allotting the subordinate P to the first task. It means that we can't assign any other subordinates to that particular task. So I'm going to cross out all the other zeros of that particular column. Then if I take any other row, let's say second row I have only 1 0 here. So let me mark there. And we have to cross out if we have any other columns, any zeros in that particular column. Actually we don't have such zeros. And if I take fourth row and third row has 2 zeros. Fourth row don't have any zero. It doesn't contain any zero. So what I have to do, I have to mark lines here. So we are going to mark this 0, and I'm going to cross out this, or otherwise you can assign this other 0 which is in third row fourth element, and you can cross out third row second 0. So now what I'm going to do is I have to draw the minimum number of lines joining the assigned zeros. So the minimum number of lines can be like this, and this is one line, and this can be another line, and you can draw like column wise or row wise. Let me draw column wise actually here. So these are the minimum number of zeros we have here. So what we have to do, we have to find the minimum entry. We have to find the minimum entry of among non-lined numbers. Non-lined entries or non-lined numbers, and we have to subtract from non-lined. Non-lined means the entries through which no line is passing, and we have to add from intersection of lines. So what I have to do is, so if I take this matrix, in this the non-lined entries are 9, 3, 3 and 15, 1. So I have to make a change here because we haven't covered this cross out 0. So let me change this vertical line into horizontal. let me change this vertical line into horizontal so that I can cover all the zeros. So now if I consider the non-lined entries 14, 9, 3 and 13, 15, 1, 1 is the least element here. So what I have to do is I have to subtract 1 from all the non-lined entries. So I'll get, let me write this as step 4. So I'll get uh, 13 here and 8 here, 2, and for the fourth row I'll get 12, 14, 0. And I have to subtract, I have to add 1, that particular 1 for the elements who are lying on the intersection of lines. So if I take second row first element 9, it is lying on the intersection, so that I have to add, so it will be 10, and this 23 also it will be 24, and what are the other entries we have to write as it is. So 22 and 24, 0, 3, 0 and here 0. So now I am repeating the same process which we did in step 3. I am going to give allocations here. So again this first row has only 1 0, so I am allotting that. I am going to strike out all the other zeros of that particular column. Now if I take second row, I am going to allot this 0, and for third row we have 2 zeros, and for fourth row we have only 1 0. So I am starting from fourth row, I am giving allocation here, and I am going to cross out all the other zeros of that fourth column, and the only remaining entry here is this 0. So my transportation schedule is my transportation schedule here is for the subordinates and tasks with the cost. So for the subordinate P, I am going to allot the task 1. For the subordinate Q, I am going to allot 3. For R 2, and for S 4, with the cost whatever is given in the question actually. So P2 1 is 8 and Q2 3 is 4, 8 plus 4, and this is 19 and this is 10. So the total cost will be 8 plus 4 plus 19 plus 10, with the total cost 10, 19, 29, 33, 41. So with the total time, actually the total hours is 41, which is optimal. But therefore the optimal assignment time or hours is equal to 41. Then question number 7. The question is, find the optimal solution for the assignment problem with the following cost matrix. So we have 4 salesmen and 4 areas. So this is the cost for reaching particular areas to the salesman. Now we have to find the assignment which gives minimum cost. We are going to use Hungarian method for this problem. Before that, we are going to check whether the problem is balanced or not. Actually, we have 4 salesmen and 4 areas. So number of salesmen is equal to number of areas. This means that the problem is balanced. So step 1 of our Hungarian method. So we have to find the least element from each row, and we have to subtract that element from all the entries of that particular row. So here the least element is 8. So 8 minus 8 0, and this will be 3, and this will be 9, and this will be 8. So the first row will become 3, 9, 0, 8. And for second row, let me write the salesman PQ RS and the areas 1, 2, 3, 4. And for the second row, the least entry is 6 here. So if I subtract 6 minus 6 0, here it will be 6, and here it will be 1, here it will be 3. So 3 1 3 1 6 0. and for R, the row R, the least entry is 12 here, so it will be 0, it will be 3 4 1. So the entries are 1 4 1 4 3 0, and for the fourth row the minimum value is 0 here, so it will be 4 0 2 1. So 4 0 2 1. So step 2. Step 2 is doing the same process column wise. So we have 4 salesmen PQ, RS, and we have 4 areas 1 2 3 4. And if I take first column, the least entry is 0. So if I subtract 0 from all the entries of that particular column, we'll get 2203. And for the second column, again the least element is 0. So we don't need to do any alterations, because 9 minus 0, 1 minus 0, 4 minus 0, 0 minus 0 remains the same. And for third column also we have already 1 0, so no changes. And fourth column also we have already zeros, so no change. Now step 3, I'm going to give assignments. So if I take this matrix from step 2, if I write it once again, I'll get PQRS and 1 2 3 4 2908 2160 0430 and 3021. So we are going to search for the rows or columns in which we have exactly 1 0. If I take first row, it has exactly 1 0. So I'm going to give the salesman P the area 3. And if I take second row, I'll be having exactly 1 0. I'm allotting salesman Q to the area 4, but we have one more 0 in the fourth column, but we are going to cross it out, because we gave this area 4 to the salesman Q. Again, it is not correct to give the same area for another salesman as well. So I'm going to strike out this another 0 in that particular fourth column. So if I take a third row here, we have only 1 0 now, so that I can allot. And if I take fourth row, I'll be having only 1 0. So no zeros, no other zeros in the corresponding columns to strike out actually. So I'm leaving as it is. So now what is my assignment schedule? My assignment schedule is here we have salesman and area with the cost. So for the salesman P, I'm going to give the area 3, and for Q 4 R1 S2 with the corresponding costs are 8 6 and 13 and finally 10. So with the total cost 37, which is optimal here. Therefore the optimal cost is rupees 37. Then question number 8. The question is, assign 4 trucks 1 2 3 4 to the vacant spaces A B C D E and F, so that the distance traveled is minimized. The matrix below shows the distance. So we have 4 vacant spaces, let's say 4 cities, and 4 trucks 1 2 3 4. If the truck 3 is going to the space C, if the truck 3 is going to the space C, it has to travel 6 kilometers, let's say 6 units it has to travel. It means that from city C, the truck 3 is 6 kilometers away. So similarly, the other entries we can visualize. Now we have to give allocations for these trucks 1 2 3 4 to the vacant spaces A to F. So unfortunately we have the number of vacant places are 6 here, and the number of trucks we have is 4. So this problem is unbalanced. This is actually unbalanced. So now what we have to do is we have to we have to add two more dummy columns to make it as balanced. So after giving two dummy columns, let's say first dummy column be D1 with all the entries 0, and the second one D2 with all the entries 0. So now what I'm going to do is I'm going to do the same process of our Hungarian method. Step 1, we have to select the least entry from each row, and I have to subtract that entry from all the entries of that particular row. So obviously we have 0. If we take any row, we'll be having a 0. So step 1 is not a mandatory thing here, as we have already 0. All the row elements remains the same. So now actually all the entries remain the same. And step 2, so we have to select the smallest element from each row, and we have to subtract each column, and we have to subtract from all the entries of that particular column. If I take the first column, the least entry is 4 here, so 4 minus 4 will be 0, 8 minus 4 will be 4, and 0 here, 3 here, 2 here, 2 here. So this is what I'm going to write here. So 0, 4, 0, 3, 2, 2. And for the second column, the least element is 2 here, so it will be 0 and 5. So let me write here directly: 5, 0, 7, 3, 1, 6. 5, 0, 7, 3, 1, 6. And for the third column, the least element is 3. So if I take 3, I subtract, I'll get 0, 2, 3, 1, 2, 4. 0, 2, 3, 1, 2, 4. And for fourth column, the least element is 3 actually. So 7 minus 3, 4, and here 2, here 6, and 5, 1, 0. And the dummy columns remains the same: 0, 0, 0, 0, 0, 0. And here also 0, 0, 0, 0, 0, 0. So now I'm going to give allotments. Step 3. So since the matrix is little huge, so let me give my allocations in step 2 matrix as well. So from there, let me give allocations. So if I take any particular row, it will have definitely more than 1 zeros, because already we have two dummy columns. No, if I take any row, definitely it will contain more than 1 zeros. So I'm going to give allocations column wise. So if I take first column, I'll be having 2 zeros, but for second column I have only 1 zero. So that's where I'm going to give my allocation. So if I mark this particular column, then I have to cross out all the other zeros of that particular row. These 2 zeros I have to strike out. Why? Because we allotted second truck to the space B, so that no other trucks can be allotted to the space B. Means I'm going to cross out all the other zeros of that particular row. Now if I take third column, again we have only 1 0, so that I have to mark in box. It means that we gave allocation there, and we have to cross out all the other zeros of that particular row. And I'm going to do this for first column now, as it has only one column, because we striked out that first entry, first row, first entry. So all the other zeros here. So now if I watch this carefully, in fourth column I'll be having 0 here, so I have to strike out these two. And now I'm going to allot the empty spaces D and E to the dummy columns. Means we are not going to give any trucks for D and E if we want to minimize the distance, actually, for the optimal distance. So my transportation schedule schedulers here we have vacant spaces, vacant spaces, then trucks with the distance. So for the vacant space A, I'm going to allot the third truck with the distance is 3, and for B, second truck with the distance 2, and for C, first truck with the distance 4, and for D and E, the dummy truck in which we have no distance here, and for F, I'm going to allot the fourth truck with the distance 3. So if I add these things, I'll get 6, 4, 10, 12. So 12 units of distance. So let it be some kilometer. Therefore, the minimum distance traveled is 12 kilometer here, which is optimal using this transportation schedule A23, B22, C21, and we are not giving any trucks for D and E, and F to 4, fourth truck to F. Okay students, thanks for watching. Hope you enjoyed the video. See you in the next one. Have a nice day. Bye.